Hi guys, Dori Jones here. Welcome to D Squared Classroom. Today we're going to talk about blood flow, which is an important factor for medical device design when it comes to the heart. So if you're working on heart devices, because often a heart device is going to be impacting blood flow in one way or another. So maybe it's designed to enhance blood flow, maybe it sits in the bloodstream, and so you need to ensure that it's not going to impede blood flow. So I'm going to get a little nerdy on you today because you really need to consider the mathematics of blood flow and the physics of blood flow when you're designing a medical device that's going to be involved in the patient's cardiovascular system. And the physicians have to make some of these considerations as well. So let's jump right in. Okay, so we'll start with the heart, the same one that we used last week. I'll add the aorta back in. Blood flows from the left ventricle into the aorta and then out to the rest of the body. So today we're going to be talking about blood flow, and that can be written into an equation of Q, or flow, equals delta P, change in pressure, over R, which is resistance. The delta P, pretty easy. It's basically your start pressure minus your end pressure through a particular tube, in this case the vessel, which would be your arteries, your veins, some kind of vascular component, and that's our pressure. Resistance is a little less straightforward. So resistance you can think of as whatever the blood flow is up against. So how difficult is it for that blood to move through the tube? And that can be written into its own equation, which is R equals 8 times L, which is the length, times eta, which is the viscosity, over pi r to the fourth. And so again, we're talking about all of the units as far as they relate to a vessel, so the length of the vessel, the radius of the vessel, and then the viscosity is how thick is the blood that's moving through it. Now you can put all of these different equations together, and that's actually what's called the Poisson equation. Poisson is just really fun to say, and that says that delta P equals 8 times L times eta times Q over pi r to the fourth. You can get really fancy with this and get into derivatives and cosines and sines, but I won't bore you with that. By the way, take a look at Poisson, hand in the jacket. He was a badass. Anyway, back to our Q equation. So Q equals delta P over R. We can incorporate our R equation, so it becomes delta P pi r to the fourth over 8L eta. If we look at our units, we've got pressure units, we've got area units, we've got pascals in there, which can be rewritten, and that includes seconds when you're adding the viscosity unit. But really, in the end, we can cancel things out and break it down to volume and time. So our units for Q are going to be volume over time. And when we're talking about the heart, we're going to talk about that in liters or sometimes milliliters per minute. And when I think liters per minute, I think of one of the most commonly used hemodynamic parameters when we're talking about the heart, and that is cardiac output. So cardiac output is essentially how fast blood is moving through the body, and a normal range would be 4 to 8 liters per minute. It does depend on the size of the patient, how much blood you have in your body. And we can rewrite the cardiac output equation as cardiac output is equal to stroke volume. And stroke volume is essentially how much of the blood in the heart is pumped out with each beat times heart rate. And heart rate we know as beats per minute. So let's look again at our units. We've got cardiac output equal to liters per beat times beats per minute. That's our heart rate. And beats cancel each other out, so we end up with the liters per minute. Again, that commonly used unit for blood flow. If we look at the stroke volume, a lot of times it's closely associated with the patient's weight. Kilograms can be rewritten in many ways to liters. And so therefore, if we used a normal patient at 60 liters per beat and 80 beats per minute, that comes out to 4,800 milliliters per minute, or in other words, 4.8 liters per minute, and that falls within our range of cardiac output. So thank you guys so much for joining today. That's sort of the basics of blood flow. I hope you'll join us again next week.